First question, how many of you knows what CQD stands for? Perfect, so for all the people, it's your lucky day, you will know what this means. And, well, we will have like Ian Baer, Kale Maynor, Mercedes Jimeno Segovia, and Isabel Rabi. So please welcome this group for Controlled Quantum Dynamics.
So first, I'd like to thank Professor Knight for giving a talk that's so incredibly relevant to what we do in controlled quantum dynamics. And we are generally interested in maintaining the coherence of quantum systems to build devices like these atomic clocks and possibly more. It's still a very new field, and as we've just seen, with any new field, people tend to make predictions. So here are a few predictions about fields when they were new. And I'd like to draw your attention to the third one, which was a massive underestimate for the potential applications of the transistor.
So what is controlled quantum dynamics? It's a field that's bringing together physicists, mathematicians, computer scientists, information scientists, and even a few philosophers. And the main idea behind it is that the way we describe the world classically is very different to the way that we have to describe the world quantumly. And when I say quantumly, I mean when we're not looking at it. The first difference is that in quantum mechanics, the system can occupy only discrete states. And as well as discrete states, there's also coherence between these states that can cause odd effects. That's maybe the cat's alive, maybe the cat's dead. But when we come to look at these systems, we always find that the cat's either alive or dead, never one of the two. And in resolving these two pictures, the idea that in quantum mechanics, we have to describe the system as a whole. We need to describe all the coherences between every possible state. Whereas classically, we can describe the system perfectly by just describing what every single part of the system is doing on its own. In resolving these two pictures, you're forced to ask a lot of interesting questions, like, does reality even exist? Can we really solve NP intermediate problems in polynomial time? Do these have any relevance to the systems we see around us? And as experimentalists, do we really have to make the system so damn cold before we start to see these effects? And it's answering these questions, testing the predictions that these questions give us, and looking for potential application of these effects that controlled quantum dynamics finds its place.
As Ian just said, and Sir Peter Knight mentioned in his talks, controlled quantum dynamics has a great potential to be the basis of a new technology. And if we look back at human history, we're particularly good at making utensils to make our life easier. Let it be the wheel or electricity. We don't only build things that help us do stuff, but also that help us think, like a computer. It's been almost a century since we started having computers. And by computer, I mean a computer machine. Because historically, a computer was a human that would sit in a desk and compute the solutions to a problem. So at the moment, our computers are based on the way we solve problems. And we have been very successful with them. They can compute things very difficult and far more complicated of what a human could calculate even in a lifetime. But for the kind of problems we want to solve at the moment, that's not near enough. We need a change. We need to go back to basics. Looking back at all the achievements, all the technological achievements in human history, we can see that many of them have been based on a careful examination of nature. So for example, look at this flower. There's so much we still don't know about how this flower absorbs sunlight and turns it into chemical energy. So this flower has an efficiency of doing this transformation and of transporting energy far, far beyond what we can do at the moment with solar cells. So what's the secret? If we look very deep into the flower, we can single out a molecule that is doing this job. And the secret of this molecule is quantum coherence. The same quantum coherence that we can see in our labs in the basement of Blackhead. So at the moment, with controlled quantum dynamics, we can study all this quantum coherence that we see in systems that we still don't understand, and we want to see how it works. Why? Well, because we want it to be the basis of a new technology, and we want, once again, the nature to do our work for us.
So if nature is going to solve the problems for us, we need to find a way to understand the answers that she gives us. In a quantum system, we can put classical inputs and we measure classical outputs, but these are inherently random. And the quantum system actually hides this information from us by the coherences. Now, what we need to find is a way to measure it. If we imagine ourselves in a pitch black room, to see what's inside, we need to turn on the light. Now, in a quantum system, in a classical world, we can safely assume that turning on the light does nothing to the system. But at a quantum level, this just simply isn't the case anymore. And when we measure something, the dynamics of the system can change. But fortunately for us, and the physicists that work on controlled quantum dynamics, over the past 50 years, we've managed to develop new techniques that we can really specifically control light and matter. And if you're working in the basement in Blackhead in a windowless room, you'll be looking at the coherences of the quantum state of matter Bose-Einstein condensates, which go down to nanokelvin temperatures. Or perhaps you'll be looking at single ions that are held in a trap. All of these highly ultra-cold, highly localized, and extremely isolated systems are perfect for studying coherences. Or perhaps you're not in the basement, perhaps you're up on level 12 in EEE getting all the sunlight. And you're thinking, and instead of working with lasers and cooling things down with liquid helium, you're thinking about quantum systems and how actually these coherences are affected by the environment. How do these change?
So at Controlled Quantum Dynamics, we're trying to utilize these quantum systems, this coherence, to do something different. And we've seen how influential manipulating this coherence was for atomic clocks. And a lot of people in controlled quantum dynamics are working towards universal quantum computers, which can do a huge raft of problems unsolvable classically. But the best thing to do is to think back to those quotes. And maybe the atomic clocks and the computers were to control quantum dynamics what the hearing aid was to the transistor. Thanks.